Welcome to Academic Gadgets class. Today's class will be treating capacitors and dielectrics. So you need to understand that when it has to do with capacitors, we say that this is an electronic device used or that stores charge. So we also say that it is a passive electronic device. The same way you know that resistor is a passive electronic device because its its functionality doesn't depend on external power source. So unlike transistors that are active devices, this one is a passive device. So if I know this is long English. I need you to know that whenever you hear capacitor, that is more like the way you normally see that definition. It's more like trying to check. You know that electric potential is work done moving a unit charge from one point to another. Capacitor, as it's storing, what happens inside it is that it is relating how much work is done on charge. So by the time a charge moves from one point to the other, supplying currents, a point will come when it gets to equilibrium. It will no longer be able to supply. In that case, all the charge in the capacitor has been discharged. So it goes to tell you how the work done on a charge is done. So that is the function of capacitor. So you need to note it. So it tells how the work done on a charge is performed. And I need you to know that charge, which is Q, is equals to currents and time. And this is gotten from the formula of current, which says that it is equals to charge time. Or we say that current is simply the rate of charge. That is how charge is moving. If it's too fast or if it's too slow, or if is it too high at a given time, or is it too low at a given time, how much of it at a given time, how much of charge at a given time is current. So from there we get this. So you also need to know also that charge is equals to NE, that is number of electron or proton and then charge of electron. So we can say where I equals to current, Q equals to charge, T equals to time. So you can note this. Then on the second part, you can note where N equals to number of electron or proton and E equals to charge of electron. So can be also charge of proton. So you know that number of proton and number of electron, they are the same thing. It's just that the charge of electron and charge of proton, the charge of electron is equal to negative 1.67 times 10 raised to power minus 19 coulomb. I should be correct. I hope so. So if I know this, we now move to Let's see what this capacitor is talking about. We know that we are still under capacitor. So we normally say that it is made up of parallel plates, that are close. It can be far, it can be near. But in some textbook, you see it's represented this way. Let's say you see something like this. So the longer side is positive, the shorter side is negative. So represented this way. This one is for battery, sorry. This is for battery. So if it's capacitor, it doesn't have any difference. So battery is simply, and capacitor is not battery. So if I know this is going to be, let's say this is the positive terminal, this is the negative terminal. This space in here can be air. The spacing, that is the distance. I'll use R, you can use D, but I want to use R. The distance here, the separation can be air, it can be water, it can be anything, but it is always an insulator. So the separation is made, no, it can't be water because water is a conductor with an insulator. So this insulator can be air, and it can be dielectrics, can be a dielectric, it can even be a vacuum. You need to know this. Now you now need to understand that the issue of capacitor and capacitance, capacitor is a device while capacitance is the attribute exhibited by a capacitor. So the issue of capacitance is simply gotten from the fact that charge is directly proportional to voltage. That is the work done in moving a unit charge from one point to the other. They are directly proportional. So when you now put this proportionality constant that you normally see, so what you have there is now the capacitance, then V. So you always need to have this in mind. So which means that capacitance in itself now will simply be C equals to Q over V. And that is why I told you that is simple. Anytime you have something at the bottom, what is at the bottom describes what is up. So you simply describe how the work done on charge is performed, how efficient is it. So, and that is capacitance for you. And at the end of the day, the device that is this capacitance helps store charge, and when it gets to equilibrium, it discharges. So we'll still get to all that. So in real life example, you always see it this way, something like this, maybe something like this. Let's say this is A, let's say this is B, and let's say I have this to be the handles. So you see that there's a space here. The spacing in between is the distance. Let's say it's distance for D because we are not dealing with radio. So let me use D. So you see it. So you need to know now, you need to know that capacitance depends on two things. Depends on one, that is A, area of charge, or surface area of charge. So if there is much area, if you increase the area, that means that the charge, that means that it will have the capacitor. If the area of the capacitor, let me use area of the capacitor. So if you increase the area of the capacitor, that means that the capacitor will have more room to store charge. And B, the distance, that is this distance apart. Remember when I drew this is like the side view, this is like the plan view. So the distance here, if it is very close, the electric field will be very close, intense. Or if it is further apart, if you remember, even when we did force is directly proportional, electric force is inversely proportional to distance apart. So if it is far, that means that it will not be, the electric field will not be too high. That means that the charge will drop, the capacitor storage will drop too. So distance of the plates, of the parallel plates. So these are the two things that determine capacitor or capacitance. So capacitance or capacitor, capacitance does not depend on voltage. So just these two things, you need to know it. So the reason I'm stating this, it's not like you have to have it in mind. But let's now go to the part where we expect, which is calculation. So before we move to calculation, I want us to relate capacitance or capacitor. I would like to use capacitance because capacitor is device. I would like to relate capacitance to four main things. So I relate it to relating capacitance to four key areas of electricity, or of of electrostatics, and that is what I normally call GEX. That is relating it to Gauss law, to electric field, to charge. So charge Q, electric field E, so and G, then to surface density. That means if you want, you can relate it to volume density or area density, whichever one. But remember, this one is for surface density. So if I know this, let me partition this way. So first of all, I will quote Gauss law says that electric field and the area is equals to, or you say electric flux, which is equals to electric field, product of electric field and the area is equals to charge, and that is charge per permittivity of free space. Why electric field itself? If you remember from the formula, V equals to ER, it simply means that electric field is equals to V over R. So if I know this, or see, I think the best way to put this is, instead of using electric field, because Gauss law talks about electric field, so Gauss law is certain as electric field. So let me say electric potential. So let me use it, electric potential, GX, electric potential. So why charge, if you've seen it, charge is equals to capacitance and voltage, that is to electric potential, and surface density is equals to mass, that is charge over area. Told you to always see charge as mass. So if I know this, I can make electric field subject of formula here, so that I have E, E is equals to, let's check. Yes, E is equals, just bring this one down, Q over E naught A. And then here, so I have V. So I can say, since V is equals to ER, that means that V is equals to, carry this and put here, Q over E naught A, then times R. Then since Q is here, since I have Q here, I have Q here, it's now up to me. I can say, let me carry this Q now that is here, let me carry CV that is here and put here. Or I can say, let me make V subject of the formula here. So let's say it's the same thing as saying, okay, let me carry Q and come here. Let me carry everything for Q and come here. So I now have C. Anywhere I see here, I put Q R all over E naught A. I see it. So which means that, notice that this charge can cancel this charge. But when you do that, you no longer have a subject formula. It's not good like that. So what we can do is to say, since we are seeing since we are seeing E, I can come here as well. So these are different ways to see. I can say, since right here charge is equals to permittivity, surface density and area, I can say that charge is the same thing as saying yes, let me replace what I have here as charge, this thing that I have here, let me replace this and this. So I can put surface density is always something like this, and area is equals to CQR all over E naught A. So these formulas, all these formulas are important depending on what they ask you in the question. So let's see. A is over 1. So you can very well see that if I want to make surface density subject of the formula here, or anything subject of the formula, I can say cross over here, so that I now have surface density is equals to CQR all over E naught A square. You can have situation like this. While if I come back here to this one, I can see that since this is QR or E naught, notice that V itself, if I make V subject of the formula here, from this formula of density, I can have that since, I can say, since Q is equals to CV, that means that V is also equals to Q over C. So I can say this V that I'm seeing here, let me replace it with Q over C. So I can do Q over C equals to QR E naught A. So let's say I want to make capacitance subject of formula, because that's the topic we are treating. Capacitor, correct, capacitance. If I want to make capacitance subject of the formula there, I can now have cross cross. So I can now have CQR equals to QE naught A. This can take care of this. Q's can take care of Q's. So I now have divide both sides by R. C is equals to E naught A all over R. So are you seeing it? So it's up to you what you want to do. And do you know that this formula is endless? Because I can also say that from any of these, sorry, from here, where I have this now, I can say that if this is the case, if I make E subject of the formula, I can say since V equals to ER, I can say E equals to V over R. So let me replace E that is here with this. So I can say V over R equals to Q over E naught E. Are you seeing it? So it's now up to me to know what I want to make subject of formula. If it's V now, you see that this will come here and it will give me back this. This will come, give me back this. If it is Q, I can say let me make Q subject of formula. So I can say Q supposed to be QR, and this QR equals to E naught A R. Or let me use R for radius too, but you know that the R there is for distance. So if I know this, making Q subject for I can have EQ. Okay, divide R, remove R, remove R. So this is the sentence saying E naught A. Are you seeing it? Yes. Okay, but notice something. This one came here, and this one, this is V, not R. V. Okay, sorry. So E naught V all over R. So you see charge is also this. So are you seeing different ways to relate this? So you don't ever get confused. Remember, we are not talking about anything but capacitance. So, but because we are focusing on capacitance, notice that all these ones I'm relating, all these things I put is like when I'm mixing Gauss law with this charge. When I'm mixing Gauss law with charge and everything, it is that I've gotten charge to be this. And everything I got here, if I come back here, I can get it. So have all these things in mind. But the most important to note is this one. This one. This is very important for you to note. And also this. Very important to note. So important. So if they ask you to find any of this, depending on what the question give you always need to think in this direction. So with this said, we can move over to calculations in future, but I want us to just remember that it is not only like, it's not every time we see. Okay, so notes. Okay, sorry, let me first do this. Capacitors in series and parallel. You need to note that it's not every time you see capacitor that is one like this. So it's not every time you see capacitor that is one like this. You've seen those representation before. It's not every time you see it this way. Just like that thing I told you when we started. So there can be cases. So there can be cases. So so are there are cases where we have more than one capacitors connected in series, parallel, or series and parallel. So we'll still do calculations on this. So for example, if I have something like this, and let's say as I have something like this, let's say I have something on this end. Sorry, I closed it. I made a mistake. It's not supposed to be closed. So told you the bigger part is always the positive, the smaller part is always the negative. Let's say I have it this way. And let's say I have another one that is this way. And notice something. If this is Q1 and this is Q2 and this is the voltage, and let's say this is Q1, Q2 and this is the voltage, notice what has happened here. Anytime you connect in parallel, you've increased the area. You've increased the area in the sense that if this is an area that charge is flowing, you now apply the parallel to get another area. You see it? But if it has to do with series, notice that this is the only thing that the charge, I know your focus will now come and be in this box instead of looking at the charge I'm showing you. Look at this. Charge is flowing here to this point. Charge is flowing now to this point. See spacing. But look at this one now. As this voltage is moving, we're doing work. Charge is flowing here. But notice that the charge that is flowing here is still flowing on this end. The same voltage, like see as this voltage is moving now. This voltage, this work that is being done, as it's moving, it will be changing. It will come here, the first point, it will be big. Come here, it will reduce because it has done work here and now doing work here. But the charge that is moving from this end to this end, watch, when this thing is positive and this is negative, as this thing flow here, and this one that is as the positive, as it's flowing to in a capacitor, charges move from, or in a metal self, charges move from negative to the positive. So as it's moving towards this end, this one as well does not move. Protons does not move. So it's moving to enter here. It will reach here, then come here. So as it enters here and enters here, is the same charge. But notice that if I have a charge here, this charge is different from this one. They are in different places. So for that reason, we say that when we are calculating for parallel, we go back to this our equation, which is Q equals to CV. It's very important to remember it. So whenever you are doing this, you need to know that the voltage will always be the same. So you say, when I'm doing for parallel, I will find charge. The charges are different. The charges are different. You need to know that. But when I'm doing for series, I'll find voltage, and making voltage such as the formula here, you have V equals to Q over C. I use this small q, I'm used to this q, small q, Q over C. So what you say here is that I want you to say, I'll find here, I'll find voltage. That's why I made voltage subject of formula. Voltage is different. Voltage different. Here, charge different. So that means that it has same voltage or same electric potential. But here, it has voltage different and then same charge. When we start calculation, you understand better. But note how we are deriving the formulas. So that if this is true, we'll now say, okay, let's say I have, as charge is moving here, I have capacitance 2, capacitance 1. Then let's say here I have capacitance 1, capacitance 2. That is storage of charge 1, storage of charge 2. And then if I know that, let's say I now have Q equals to, because I'll find Q here. So that means that Q will simply be Q1 plus Q2 plus Q3 plus dots will give me total Q. So if I know this, but see, C1 now, voltage is the same. So C will now be C1 plus C2 plus C3, because notice that in each charge there's capacitance. So plus dots will give me total C. But voltage is the same. So for that reason, let me bring this Q now that is here. So Q is CV is equals to, I'll have C1 plus C2, that is Q, that is total Q or equivalent Q, yes, is equals to CV. So plus C3. Now notice something. As C is changing, voltage will remain the same. That is, will remain the same. So that means that this voltage can cancel this voltage. So that I have C, total C, to be equals to C1 plus C2 plus C3. You see it? Total C, total V. And you can get it this way too. So while this side, Q is the same. But V will now be, total V will simply be equals to V1 plus V2 plus V3. Are you seeing it? And total C, now to get total C, let's use the formula. Notice that V is given by Q over C. So I will have V1 plus V2, because it's different in this case, plus V3 will be equals to, and everything, okay, plus dots is equals to total C. So will now be equals to, Q will be different, Q over C1 plus Q over C2 plus Q over C3. Now notice something. If I know this, we normally say that, we can say from here, the equation V is equals to Q over C. That is total V, total C, total this. So that means that if I replace this now, it will now be QT over CT will simply be equals to Q plus Q plus Q over C1 or C2 all over C3. So you see that the Q and Q that I have will be the same, because Q, will say that Q does not change. The charge, when charge is flowing this way, doesn't change. As we do examples, I'll show you. So this will cancel this, cancel this, cancel this. So since it cancels, this is now carrying 1. Therefore, charge, therefore capacitance on a capacitor in series is given by 1 over C1 plus 1 over C2 plus 1 over C3 plus dots, so and so on and so forth, 1 over C total. Are you seeing it? Yes. So remember, this side is 1 over C total. Same thing. So go through it over and over. So in our next class we'll do problems so you understand it better. Thank you.